Hi. In this video, we are going to solve an example to show how to apply Fourier Transform to discrete-time linear time invariant system. In this example, the discrete-time linear time invariant system is described by the difference equation y of n minus 0.5 yn minus 1 is equal to x of n. That's the difference equation. The first question is determine the frequency response h of omega of the system. So, what is the frequency response of the system? If you have a linear time invariant system, represented by this block diagram, that's the linear time invariant system, and the input is x of n, and the output is y of n, and the impulse response defined by h of n. If you want to find the frequency response h omega of the system, so you got to transform this by Fourier transform to x of omega, and the output y of n to y of omega, and also will be h of omega. What is the relationship between the input and output? It's h omega. H of omega is equal the output divided by the input. So to do that, we have to convert this difference equation from time domain into frequency domain. Y of n, it will go, let me write the equation here again. Y of n minus 0.5 y of n minus 1 equal to x of n. We know that y of n by Fourier transform of discrete, of course, that will be y of omega. What about if you have time shift like yn minus 1? We have to review the property. There is a property of time shift said that y of n minus alpha, the Fourier transform will be equal to y of omega and multiplied by e to the power of minus j alpha omega. In this case, we have alpha equal to 1. So y of n minus 1 will be transformed to e to the minus j omega y of omega. So the same thing, now we have only x of n will go to x of omega. So I will write the equation in frequency domain now after this conversion. Y of omega minus 0.5 e to the power minus j omega y of omega equal to x of omega. Now I will take y of omega as a common factor. So what's left here? 1 minus 0.5 e to the power of minus j omega. On the other side we'll have x of omega. Now to find h of omega, you will divide y of omega by x of omega, the output divided by the input. So it will be 1 over 1 minus 0.5 e to the power minus j omega. So what we got here, the frequency response of the system, and that was the first question. H of omega, frequency response of the system. The second question here, they're asking about find the impulse response. Usually it's a function of time, hn. So all what we're supposed to do is just to convert this one by inverse of Fourier transform into h of n. So how can we do that? You go to the table and you look for some formula that's close to this expression. We found out that in the table, if you have a constant power n un, that will be transformed to 1 over 1 minus a e to the power of minus j omega. So in this case, the alpha is equal, or a is equal to 0.5. So you can write directly y of n will be equal to a, which is 0.5, power n un. So that's the impulse response of the system, time domain. Of course, it's easy, but I'd just like to remind you, sometimes maybe you can have this like a little bit complicated, so you can use partial fraction. But this is simple just to show the idea. Now, we're done with the second part. Let's go for the third one. Determine its response y of n. It means you want to output when the input is equal cosine pi over 2n. So the system now, the input x of n is given as cosine pi over 2n, and it's required to find the output. It's given, we know for the system, both the impulse response and the frequency response. Well, of course, it's better to use the frequency domain to solve this problem. So we'll say that the output is equal to x, the input, time the frequency response of the system. We have this already. H, we found it equal to, here you go, 1 over 1 minus 0.5 e to the power minus j omega. X, we don't have it, but we have it in time domain. So all what we're supposed to do, again, we have to go to the table and see how we can convert the cosine. So we look at the table, found that cosine alpha n using Fourier Transform, it will be equal to pi delta omega minus alpha plus delta omega plus alpha. In this input, alpha is equal pi over 2. So now we can write x of omega is equal pi. I will distribute pi over both. Pi delta omega minus pi over 2 plus pi delta omega plus pi over 2. So that's the Fourier transform of the input. To make it easy, we'll just call this x1 of omega, and that's x2 of omega. And we use linearity property just to make it easy, because I don't have enough space here on this page. Now I want to put x here with h, so I will have y. I will not write omega to make it fast. Y is equal x, and you know x is equal x1 plus x2 times h. So you have x1 h plus x2 h. This is, call it y1, and this call it y2. I will take the first one. Y1 is equal x1 times h, and this is x1 pi delta omega minus pi over 2 times h. I will write it h like that, h of omega. Now I'm going to use the property of impulse. When you multiply delta, we have this before in time, you know, remember this one, the second one too? Delta t minus alpha, if you multiply by any function of time, or any variable, doesn't have any time. So to be equal, you write the same delta t minus alpha, but f of t, you substitute by t by the value of alpha, f alpha. That's what we learned before, you know, early, very early in the course. Well, I'm going to apply this. to y1 and y2. So y1 will be equal to, I will write the same equation, that's constant, it doesn't affect. And then this is delta function, delta omega minus pi over 2. H now will be h, I will replace omega by pi over 2. All right. Now let us look what's h of pi over 2. First, you have to write the expression for h. I have h here, I think. Right here. Yes, that's h. 1 over 1 minus 0.5. 1 over 1 minus 0.5. E to the power minus j omega. Now, omega, I'm going to replace it by over 2. All right. I'd like, just to simplify this expression for h pi over 2. Because I have a complex number here. First, this one it looks easy. E to the power minus j pi over 2. It's equal to cosine pi over 2 minus j sine pi over 2. Cosine pi over 2 is equal 0. Sine pi over 2 is equal 1. So it's equal minus j. Now it's really easy. So let's just simplify it. And we'll write that h of pi over 2 will be equal to 1 over 1 minus 0.5 multiplied by minus j, so that plus j. All right, so h of pi over 2 is equal to 1 over 1 plus j 0.5. I still can make it more, this guy, complex, I can represent it in polar form. I can say 1 plus 0.5 j. I take the absolute value, square root, get the magnitude. The magnitude, it's equal to 1, I rounded, 1.12. And the angle, would be 10 minus 1, if you write the angle, theta, where theta will be equal 10 minus 1, the imaginary over the real, which is 0.5. I did that in the calculator. In radian, I found it is equal to 0.436 radian. All right. So you can express this complex number converted from Cartesian to polar form. So you can write 1 plus j 0.5 equal to the magnitude, which is equal 1.12 e to the power, the angle, you make it j, all right, 0.436. Great. So that's, the value of it. So let's just, now put it in h. H now will be equal to, I'm talking about h of pi over 2 is equal to 1 over 1.12 e to the power j 0.436. Okay. If you do that, so you might write it 1 over 1.12, it will be 0.89. And this one will go up, be negative, e to the power minus j 0.436. I'm done with h pi over 2. Remember, it's part of y1. Part of y1, it's this one times pi delta omega minus or equal to. Okay, so you have now y1 equal to this number 0.89 times pi delta omega minus pi over 2 e to the minus j 0.436. y2 will be similar, except only it's different in the sign. So save your time. I'll tell you how you do it. Delta, you have here positive, here both positive, and the sign was here different, so be e to the power plus j instead of minus j 0.436. You got y1, and this is y2. You add them, you get the y total. But when you want to find the response, it should be y of n, function of time, not the frequency. But this helps us to find it, as you saw. So let's just convert one by one. So how we convert y1 of n? You got to look at this formula or this expression and see something similar. So when I look at the table, I found something close to this one. What I found is like the function e to the power j alpha n, if you convert it by Fourier transformation, it would be 2 pi delta omega minus alpha. That's what we found in the table. All right. So you have pi here. So you can multiply by 2 and divide by 2. So you have this 2 here. And the constant, leave it as it is. So let's just write y1 of n. Just a second, we'll get it back here. 0.89, that's the constant, 0.89. And you got divided by 2 here. So you can keep the 2 pi delta omega minus pi over 2. So your alpha is equal pi over 2. So the conversion will take this one, will be equal to e to the power of j, and alpha is equal pi over 2 times n. And would miss anything? No. Oh yeah, there is a constant, another constant. This is constant, e to the power minus j. It's a number, just a constant. E to the power, it's a second here, e to the power minus j, and I think the number 0.436. All right, so we got it right here. Yes, that's right. All right, now you can simplify this by you divide 0.89 by 2, so you have 0.445, and e, you take this one like j is a common factor. What's left here? That's pi over 2n minus this number. It's a constant, 0.436. Great. When you do y2n, to save your time, it'll be the same. Just, the sign is at 0.445 e to the power b minus j pi over 2n minus 0.436. Then you add both. All right, you add both. Oh, by the way, let's just leave this one without calculating. Let's just leave it as it is, 0.89 over 2. I will leave it. I'll tell you why now. Now you add both, so we have y of n is equal y1 plus y2. I will take common factor this one, 0.89 over 2. And you observe this number, the same number, but just j plus and j minus, but both are the same. Call it let's call it another angle like phi, for example. So you have e to the power j minus or plus, the first one, plus j phi plus e to the minus j phi. And this 2, you can take it here. That's why, see, I left it here. This formula represents the cosine. So you have 0.89 cosine phi. Now I go back and find what's my cosine. This is my cosine, my phi. So the final answer will be y of n will be 0.89 cosine pi over 2n minus 0.436 radian, of course. And that will be the answer, the final answer. So, yeah, it was a little bit involved, but it's a good example to find the response, especially that the input is cosine wave. Okay, thank you for paying attention.